Welcome to Agentic AI World, your daily interview prep for senior AI engineering roles. I'm your host, and today we're diving into episode 83, AI Transfer Learning Deep Dive, how senior engineers master domain adaptation and knowledge reuse in modern AI systems. Let's get into it. Section 1. What is transfer learning and why does it matter? Transfer learning is one of the most powerful concepts in modern AI engineering. The core idea is simple. Instead of training a model from scratch on every new task, you start with a model that already knows a lot, typically trained on massive datasets, and you adapt it to your specific problem. Think of it like hiring an experienced engineer. They don't need to relearn programming from scratch. They bring years of knowledge, and you just orient them to your code base. In AI, this translates to enormous practical advantages. Training a large language model or vision model from scratch costs millions of dollars and weeks of compute. Transfer learning lets you achieve comparable results in hours on a single GPU with a fraction of the data. This is why, in your senior engineering interviews, transfer learning will come up, not just as a concept, but as a system design challenge. Interviewers want to know, given this business problem, how would you use transfer learning to get there faster, cheaper, and more reliably? Section 2. The 3 core strategies. There are 3 primary strategies in transfer learning, and knowing when to use each one is what separates a senior engineer from a junior one. Strategy 1. Feature extraction. You take a pre-trained model, freeze all its weights, and only use it as a fixed feature extractor. You feed your data through the model and grab the intermediate representations, the embeddings, then train a simple classifier or regressor on top of those features. This is the right choice when you have very little labeled data. We're talking hundreds to a few thousand examples. The pre-trained model's representations are already excellent, and you don't have enough signal to justify changing them. Classic example: using a ResNet or VIT trained on ImageNet to extract features from medical X-rays, then training a small logistic regression to detect pneumonia. You get strong performance without risking catastrophic forgetting on your tiny dataset. Strategy 2. Fine-tuning. Here, you unfreeze some or all of the pre-trained model's layers and continue training on your target dataset. You update the weights using a small learning rate to preserve the pre-trained knowledge while adapting to your domain. The critical engineering decision is, which layers do you unfreeze? The standard wisdom is that early layers capture universal features, edges, textures, basic syntax, and later layers capture task-specific features. So you typically freeze early layers and fine-tune the later ones first. If you have enough data and the domains are very different, you gradually unfreeze more layers. In large language models, this is called instruction fine-tuning or supervised fine-tuning, or SFT. You take a base model like Llama, provide examples of the behavior you want, and fine-tune the model to follow instructions in your domain. Strategy 3. Parameter-efficient fine-tuning. This is the cutting-edge approach that's become standard for large models. Instead of updating all the weights, which can be billions of parameters, you inject a small number of trainable parameters into the model and only update those. The most popular technique is LoRA, low-rank adaptation. You decompose the weight updates into 2 small matrices, which together represent a low-rank approximation of the full update. This reduces trainable parameters by a factor of 10,000 or more, while achieving comparable performance to full fine-tuning. Other techniques include prefix tuning, prompt tuning, and adapters. They all follow the same principle. Keep the original model frozen, add a tiny amount of trainable structure, and train only that. This is production gold. You can fine-tune a 70 billion parameter model on a single A100. You can maintain multiple domain-specific adapters and swap them at inference time without loading separate full models. Section 3. Domain adaptation, the hard problem. Here's where things get interesting for senior engineering interviews. Transfer learning is easy when the source and target domains are similar. ImageNet to medical images, fine. English Wikipedia to English customer service emails, fine. But what happens when the domains diverge significantly? This is called domain shift, and it's the core challenge of transfer learning in production. Consider a model trained on English text applied to code, or a model trained on news articles applied to social media. The vocabulary, syntax, style, and factual distribution are all different. There are several techniques senior engineers use to handle domain shift. Domain adaptive pre-training, or DAPT. Before fine-tuning on your labeled task data, you continue pre-training the model on your target domain's unlabeled data. This adapts the model's representations to the new domain's statistical patterns before you ask it to learn your specific task. This is especially effective for specialized domains like legal text, medical literature, or source code. Multitask learning. Instead of fine-tuning on a single target task, you fine-tune on multiple related tasks simultaneously. This forces the model to learn more general representations that transfer better across variations in your target domain. Domain adversarial training. You train the model with an adversarial objective that encourages domain-invariant representations, features that are useful for the task but cannot distinguish between source and target domains. This is particularly powerful for structured domain shift, like adapting a model from synthetic data to real-world data. Section 4. Production engineering patterns. Let me give you the patterns that come up in system design interviews around transfer learning. Pattern 1. The adapter stack architecture. In production, you often need one foundation model to serve dozens of downstream tasks. Loading a separate fine-tuned model for each task is prohibitive. The solution is an adapter stack, one frozen base model, with task-specific adapter layers loaded dynamically per request. At inference time, you load the appropriate adapter into a shared model server, process the request, and return the result. The base model weights stay in GPU memory continuously. Only the tiny adapter weights are swapped. This reduces memory overhead by orders of magnitude. Pattern 2. Progressive fine-tuning. Rather than fine-tuning directly on your final task from the pre-trained checkpoint, you fine-tune through intermediate tasks that bridge the domain gap. This is also called curriculum transfer learning. Example: you want to build a medical diagnosis system. Start from a general language model. Fine-tune on biomedical literature. Fine-tune on clinical notes. Fine-tune on your specific diagnostic task. Each step prepares the model for the next, reducing the risk of catastrophic forgetting and domain shock. Pattern 3. Continual fine-tuning with replay. One of the biggest dangers in production is catastrophic forgetting, when fine-tuning on new data causes the model to forget what it learned on old data. The solution is experience replay. You maintain a small buffer of representative examples from previous fine-tuning rounds and include them in every new training batch. This keeps the model anchored to its prior knowledge while it learns new skills. Pattern 4. Evaluation before and after transfer. Senior engineers always evaluate transfer quality on multiple dimensions: in-domain performance on the target task, out-of-domain performance on related tasks to check for regression, and representation quality via probing classifiers to verify that the transferred features actually encode the right concepts. Section 5. Interview questions and model answers. Let's run through the questions you'll face. Question: how would you decide between feature extraction and fine-tuning? Answer: I look at 3 factors. Dataset size. If I have fewer than 10,000 labeled examples, feature extraction is safer.